Year 2 book, exercise 2D, question 12. A function f, which is made up of two algebraic fractions, and we've got to combine them and simplify it into a single expression like this here. Okay, and the domain of f is restricted to being numbers greater than 4. So let's start by processing that original function as given. And it's a show that question, so we have to put all the steps in to get all of the marks. So no shortcuts. So we're going to start by expecting that the denominator of this will factorize, and it will factorize into x minus 4 and x plus 5. That's what we're looking for, because that would be logical in the context of this question. In fact, it does factorize like that. So what we do is we say f of x is equal to, well, it's going to be, I'm going to start expanding out the top line actually, because we're going to need to do that later anyway. So let's start doing it now. 3x plus 6, and the denominator is going to be that pair of factors that we just mentioned. So it's going to be x minus 4 and x plus 5. Okay, so that's the first part. And from that, we have to subtract the other algebraic fraction, which is going to now become 2 lots of x plus 5. Okay, and the reason I'm doing that, of course, is because I can now give it the same denominator as I gave the previous one. Okay, so that denominator can go underneath this one now. Okay, because I'm looking for a common denominator, so I can simplify it. And that goes there. Okay, and I can now say that the subtraction of those two could be combined into a single fraction with a numerator of 3x plus 6 minus, let's put the whole thing in full, 3x plus 6 minus 2x minus 10. Okay, and once again, all of that appears over a common denominator of this. Oops. So we put that in there. And the next step, of course, is to combine all that on the top to give us, in fact, x minus 4. Now again, we were kind of expecting that to happen, because that's where the question is ultimately leading to. But nevertheless, we do still have to show all the steps. So x minus 4, and that goes over the same denominator again. Like that. And of course, the final stage would be just to take out the common factor of x minus 4 from the numerator and denominator, leaving us with 1 over x plus 5. Okay, and that's the answer we were required to give. And we just need to add that it's 1 over x plus 5 and that x is greater than 4. Okay, right, so that x greater than 4 is part of the definition of the function, you see. We know x could take any value, except of course negative 5, which would make it invalid, but any other value of x would work. But for the purpose of this function, it only applies to values of x greater than 4. All right, so part B, we have to find the range of f, the range. Well, look, the range of f is going to be determined by we're looking at all the possible values that x can be. So let's start at the lower end. X is 4, or just above 4. So let's suppose we're at 4. 4 plus 5 is 9, 1/9. Okay? Now, as x gets bigger than 4, this will get smaller. You see, when x is, say, 100, we've got 1 over 105. When x is 1,000,000, we've got 1 over 1,000,005, which is even smaller. In fact, if x was infinitely big, this would be approaching 0. So the value of that function, when x is greater than 4, ranges between 1/9 down to 0, but not including either of them. So we would define the range as, usually we put a curly bracket like that with all the values in. We would say that f of x is always going to be a real number. Okay? And this is the range, remember. So it's f of x, not x. It's a real number, and it's in the range 0, not including 0 though, f of x and the maximum value, but again up to but not including 1/9. Okay, so that's a full and thorough definition of the range of f. Now in part C we've got to find the inverse function. Now we're going to look at graphs of these in a minute, but I'm just going to start by going through the process of inverting the function. So we say that y equals the 1 over x plus 5. That's the first step. Okay, we're going to now multiply both sides by x plus 5. So I'm going to say that yx plus 5y equals 1. Okay, I'm going to now, because I'm wanting to get x on its own, so I'm going to take away the 5y from both sides. So my next step would be yx equals 1 minus 5y, and finally I divide both sides by y, and I get x equals 1 minus 5y over y. And just one other thing I'm going to do, I mean that is correct, but when we're going to explore the range or domain of a function, we'll need to do that to give the full definition of this. Okay, it's best to try and get it with the minimum number of occurrences of the variable as possible. At the moment I've got y appearing in here twice, but actually if you just split that into two fractions, you get y appearing just once, because you'd have 1 over y minus 5. Okay, and it's better to have it in that form. It's easier to see what will happen. Now, when we write the definition of an inverse function, we normally give it in terms of x. So we simply just rewrite that, replacing y with an x. And I would say that f to the minus 1 of x, okay, the inverse function of x, is equal to 1 over x minus 5. Okay, so that's the actual definition of the function, but we need to complete it by giving it its domain. And now I'm going to bring in the graphs that I've talked about, and of course you would be looking at this on your graphics calculator, hopefully quite early on in the process. So if I just bring that in now, there, you can see that the red line is the original function f of x. Okay, and you should recognize that it's a transformation of the graph 1 over x 5 units to the left. Okay, because that's a transformation of the graph. If 5 is with the x, it's a plus 5, which causes it to go 5 to the left. So the asymptote that would normally be the y-axis is now the line x equals minus 5. Okay, and of course you should know the reflection of a function in the line y equals x gives you the inverse. So the blue is the inverse function, which we've got here. Okay, so what I'm going to do is consider that the fact that the domain of f becomes the range of f to the minus 1. Okay, now the domain of f was x greater than 4. Okay, so it was this part here, if you like. Okay, I'll just sort of highlight it like that for you. So it was the bit between there and there, which was 1/9. That was the actual distance between those 2 points, 1/9, which we discovered earlier. Okay, and this line continues on getting closer and closer to the x-axis, but never reaching it. Well, if you flip all that over, it takes you to this bit here. So this is reflecting in the line y equals x, and this is the corresponding piece of graph that's been reflected from here. Okay, and that becomes the domain of the inverse function of f. So to cause the output or the range of the inverse function to be greater than 4, the domain has to be just here between 0 and 1/9. Okay, so what I have to do here is say that, so following this, I should give the full definition of the domain, which is that x is a member of the real numbers, and you possibly wouldn't need that part of it, but you should say that 0 is less than x is less than 1/9. Okay, and that's very important that you include that in the definition of the inverse function. All right, and I took that really from what we did earlier here when we found the range of f. Okay, so obviously x could take other values. We know that x could be values anywhere along here. All these values would give rise to all of this blue stuff here, but we can't include that because the range of this is the domain of this function f dashed of x is determined by the range of the original function f. Okay, and that answers that question.